Someone is praying for you. Someone is praying for you. So when it seems you're all alone and your heart will break in two.
Hello, welcome to our lessons on ordinary differential equations. In our previous lesson, we looked at higher order differential equations, and we learned that second order going are all classified as higher orders. Now, our main aim is to be able to solve higher order differential equation. But before we can do that, we have to be able to write down the characteristic equation of it. So in this video, we are going to look at how to write down the characteristic equation of any higher order differential equation. So let's consider an nth order homogeneous linear differential equations of this form as indicated in equation 1, where an up to a naught are all real constants. So we are looking at equations with constant coefficients. That's the thing I have to talk about. We are looking at equations with constant coefficients. They mean this is constant, this is constant, this is a constant, this is a constant. And to find the solution, we look for this familiar type of a function. In order to be able to find the solution to this and come up with the characteristic equation, we need a familiar type of function f, which is having a property in such a way that the various derivatives is just being that each function will be multiplied by a certain constant lambda I. And when you get that function, the resulting products of such functions when added should be equal to 0. So in other words, when you get that function and then we take the various derivative and put them inside it, we should be able to get 0. So we look for a function whose derivatives are constant multiples of the function. And that function must be in such a way that the k derivative of f of x should be the lambda raised to the power k times f of x, where lambda is a constant. And one of such a function is the exponential function. Consider in exponential function, this one, f of x equals e raised to the power lambda x. If I take the first derivative, I'm going to get lambda e raised to the power lambda x. If I take the second derivative, I'm going to get lambda squared e raised to the power lambda x. If I take the third, I'm going to get lambda cubed e raised to the power lambda x. So this is the type of function we are looking for. So if you consider a second order differential equation y prime prime plus p y prime plus ky equal to 0. Then if we substitute, if we make y, we let y to be equal to e raised to the power lambda x, it means y prime is lambda e raised to the power lambda x, and y double prime is lambda squared e raised to the power lambda x. So we put this inside this equation. Let me call this one equation 3. If you put it, you're going to get lambda squared e raised to the power lambda x, that is y double prime for this, plus p lambda e raised to the power lambda plus k e raised to the power lambda x. Sorry, here too is lambda x, and is equal to 0. And if you look at this equation, the common factor is e raised to the power lambda x multiplied by lambda squared plus p lambda plus k equal to 0. So this is a product of two functions equal to 0. And when the product of two functions are equal to 0, we say either both are 0, only one of 0. But we know for sure that exponential functions are never going to be equal to 0. So that means we only have lambda squared plus p lambda plus k equal to 0. And this equation that we are having here is what we call the characteristic equation, or auxiliary equation for this. second order ordinary differential equation. In a similar manner, if I have a third order equation, y triple prime plus py double prime plus qy prime plus ry equal to 0, and having y equal to e raised to power lambda x, y prime equal to e raised to power lambda e raised to power lambda x, y double prime equals to lambda squared e raised to power lambda x, y triple prime equals to lambda cube e raised to power lambda x. Then we are similarly going to have e raised to power lambda x multiplying by lambda cube plus p lambda squared plus q lambda plus r equal to 0. And for that matter, we are saying that since this is not going to be 0, this cannot be equal to 0. You have lambda cube plus p lambda squared plus q lambda plus r equal to 0. Which is going to be the characteristics equation of the third order differential equation. So if you look at the trend of what is happening, you realize that for the second order, y double prime plus py plus qy prime plus ky equal to 0. The characteristic equation is lambda squared plus p lambda plus q equal to 0. And you can check that the order of the derivative goes to the degree of the polynomial. So second order, second degree, first order, first degree, zero order, zero degree. Similarly for the third order, plus py double prime plus qy prime plus ry equal to 0. The characteristic equation is lambda cube plus p lambda squared plus q lambda plus r equal to 0. So this is the characteristic equation for this, and it continues like that. 4 further, we get lambda to the power 4 and so on and so forth. Let's check out a few examples. Write the characteristic equation for the following differential equations. So the first one is this. So the auxiliary characteristic equation for lambda squared, because the y prime goes to this, plus 5 lambda plus 1 equal to 0. You pick the second one, is the third order. So lambda cube minus 2 lambda squared plus 7 lambda minus 2 equal to 0. You pick this, going to the lambda to the power 5 minus 4 lambda squared plus lambda equal to 0. And the last but not the least, you're going to get lambda to the power 4 plus 7 lambda cube minus 5 lambda squared minus 2 lambda plus 1. Plus 5. That will give us 0. So that is the characteristic equation of this equation.